Yeah. A very good evening, everyone. It is my pleasure to welcome you all to the day 2 of the 5-day International FDP on Future Generation Networking, organized by the Presidency School of Information Science. After an insightful first day, we are excited to continue our journey of knowledge and innovation with yet another distinguished speaker. Before we begin, I would like to extend my sincere gratitude to all the participants, faculty members, and organizers for their continued enthusiasm and support in making this FDP a success. Your active engagement is what makes this event truly meaningful. Now, it's my honor to introduce our esteemed speaker for today's session, Dr. Jorge Garza-Ulloa. Dr. Garza-Ulloa is a highly accomplished academician and industry expert with an impressive background in electrical and computer engineering, biomedical engineering, artificial intelligence, and technological innovations. He holds degrees from prestigious institutions, including Monterey Institute of Technology and Higher Education, ITESN, University of Massachusetts, and the University of Texas at El Paso. Currently serving as an academic professor at the University of Texas at El Paso and ITESN, Dr. Garza-Ulloa is also a CEO of Research Consulting Services, where he leads groundbreaking research in AI-driven solutions, computer mathematical models, and biomedical engineering advancements. His contributions to research and academia are extensive, with numerous publications, including books and research papers on biomedical engineering, AI methodologies, stress, anxiety, neurological disorders, and renewable energy innovations. His work has had a profound impact on medical innovations, industrial process optimizations, and environmental sustainability. Additionally, as the CEO of Micro ATech, DCV Computech, he has pioneered manufacturing 4.0 technologies, AI-based process optimization, and innovative industrial solutions. His role as a board of member of the energy cluster of Chihuahua, Mexico, highlights his contributions towards renewable energy solutions and sustainable development. With such an extensive and diverse expertise spanning multiple domains, we are privileged to have Dr. Jorge Garza-Ulloa with us today. His session will undoubtedly provide us with deep insights into our future technologies, AI advancements, and their real-world applications. Once again, I extend a warm welcome to our distinguished speaker today and to all of you for joining today's session. Let us make the most of this opportunity to learn and engage with cutting-edge research and innovations. Thank you. We welcome you, sir. Over to you, Dr. Jorge Garza-Ulloa.
Perfect. Thank you. Good morning. Good afternoon. Sorry, right here on my place is almost in the morning, and you are in the afternoon. Let's go to begin with quantum networking, next frontier on communication. We're going to cover these topics. Number one, quantum internet. Quantum internet is we're going to visualize as an emerging technology. We're going to show the concept. Then we are going to focus on quantum communication, and I will focus more on the network problems. And number three, the quantum networking. We're going to cover the four main stages. One is the quantum key distribution, QKD. The other is the quantum repeaters, QR. The quantum memory, QM. And the quantum entanglement sources. It's very important. I'm not going to give you some examples of using machine learning, deep learning for advanced cryptographic application. And by the end, we're going to focus on the definition of quantum information network, QINs, and mention the concept. Just to be sure that we are synchronized, I want to include this small slide. What a qubit is. I know that almost everybody right there know what it is. Okay, we are going to explain a lot the block sphere. This is the representation of the qubits. This is the fundamental of the quantum computer. Okay, and this is the bracket notation that we're going to use. Okay, this is only for a review, and we have to focus on to understand very well about the phenomena on quantum computer that include three state superposition, the one that we are showing right here, the quantum entanglement, when we have two particles, photons, that must be, we cannot explain the behavior of one without the other, and the quantum interference. That means that if they are in phase, their amplitude is going to be up, and if they are out of phase, their amplitude is going to be cancelled. This is only a review. Now we begin right here. This is the most important thing. The things that are coming, we need to be with an open eye, with an open mind. That the classical internet, we use bits, and the quantum message, we are going to use qubits. On the classical communication, we know about the internet, everybody is using, and we are using right now. But what about the quantum communication? The quantum communication, we're going to use some QKD. That means it's a special super dense coding of cryptography to avoid interference and security, and improve security. And also, we're going to call it quantum internet. Okay, right here I have a summary of the quantum internet. Quantum internet is an emerging technology that allows remote devices to communicate quantumly through quantum data. That's important. The QUINT technology aims to provide private and secure communications by utilizing a concept derived from quantum mechanics to surround the constraint of conventional interconnect technology. And I am going to explain the 5 more important issues. The number 1 is the inability to replicate qubits. When we are in communication, we don't want to replicate the qubits. The qubits must be secure from the beginning to the end. Okay, this is the main, this is going to have many advantages over the conventional internet. We're going to focus always in quantum cryptography based on the use of no cloning principle. What does that mean with no cloning? We don't want to clone everything. Okay, we want communication and secure communication from one place to the other. These features are crucial on maintaining data confidentiality and integrity. When this assures us to make the message unreadable, unauthorized until they reach the final parties. On the number 2, the quantum networking QKD, resolving insecurity by enabling secure access to cloud-based computers using multiple protocols. Okay, we're going to discuss some of them. This is the most widely recognized implementation of the quantum networking. I am going to use a lot the QKD instead of the complete name. Okay. The QKD is the protocol that resolves the issue but enables secure access to the cloud based on computers using multiple protocols. The number 3, the exchange of information network. Okay, yeah. On the number 3, we are for the exchange of secret keys in a long-distance QKD network with trusted nodes are now feasible now with ultra-secure protocols based on quantum physical law. Okay, we're going to make examples about this. And the number 4 is the quantum information network. That means that we are going to enhance computer over the distance. And finally, the quantum state teleportation. This is a very important issue. It's the fundamental mechanism of the QIN. That means the quantum information network. One very important is to explain the concept of quantum internet containing the potential for security, multi-party computation, and distributed quantum computing, while quantum teleportation enables quantum state transfer. I want to make a comment right here. The quantum teleportation is a technique for transferring quantum information from a sender at one location to a receiver in some distance away. Now, teleportation is commonly portrayed in science fiction as a means of transfer physical object. This is not the case. We are not transferring physical object. We are transferring the quantum information. This is important. Note that the sender neither know the location of the recipient or know the quantum state that will be transferred. Everything is secure around the quantum state teleportation. Okay, and we are going to see a lot of advances that is growing and growing on the stage of quantum network. They use a lot of trusted repeater, and they use a methodology for prepare and measure. They have some special feature like entanglement, generation sources, and quantum memory. This is going to form the system that we're going to explain today. And we have few qubits fault tolerant to be sure that all information is secure. And of course, the quantum computer. The main goal is to use the quantum computer. And on the right side, you're going to see the quantum key distribution, the QKS, and the quantum key distribution, secure identification, the protocols, and the binding. Of course, everything must be synchronized using distributed quantum computation. And it's a leader election on this agreement. And then we have to explain with more detail everything that we're going to focus. The quantum communication provides a secure method for long-distance communication. This is the main issue. Its key feature includes secure quantum communication and teleportation. That means that are unique. They don't have classic analogs and unconditional secure quantum cryptography. That means that we're not going to use the classic method, and we are going to use a secure quantum cryptography. On the number 3, if we have the quantum communication offer information theoretic security for relying on physical law. Okay, I'm going to explain a little bit more. That means that it can be transmitted to quantum network like photonic chips, optical fibers, and free space channels. Okay, on quantum, everything is about the photon. It's not about the electron. It's not about the electrical or the electromagnetic. It's about the photon. And the main goal of connecting quantum computers is to build a quantum network. This is the main request that you made today, to make a visualization of what is coming. Okay, this is going to increase the computer power and enable the realization of the quantum internet, especially with processor with a few qubits. That means that we are going to combine a lot of processors, quantum processors with few qubits to analyze something bigger. And finally, introduction of quantum information technology as a global require a quantum network. This is the method that I'm going to explain from 1 to 5. Now, I want to focus the quantum information, on the other hand, is more difficult to transmit, detect, and preserve than classical. Right now, we are very familiar with internet, but with quantum information to transmit that is not so easy. And because of the inherent fragility and the quantum mechanical load that forbid replication. When we send in a message right now for internet, the message can be divided in many X parts, and the source is going to send it, and the receiver is going to receive it even on different order. They have to accommodate. This open a space to have intruders. We don't want that on quantum information. Okay. Now let's go to talk about the quantum network that we are going to explain at this time. We have two primary regimens, two primary problems. One is the external coherence. This occurs when the result of that defective device is striven to maintain and operate a quantum system. Everything can fail sometimes. That means that we need to avoid the external decoherence on the devices. And the other primary regimen is the internal decoherence. That means introduced by quantum system alone, communication by itself. Okay. Oh, bueno. Sorry. Okay, again, the quantum key distribution is going to be the crucial aspect of the quantum cryptography. That means that everything is going to be under cryptography, typically using free space and fibers. The QKD is fundamental based on the fact that the quantum information is coded on the degrees of freedom. That means on the qubits diagram that I showed at the beginning, like a preview, we have to check everything what is going on the qubits. Okay. The QKD is fundamental based on the fact that quantum information is coded in the degrees of freedom. As I told you, that means that we have polarization states of individual photon, which prevent successful attempt to measure and clone a quantum bit. From there, it's going to begin to be very protected. And at this time, researchers have developed new protocols. One is the EV1 and BBA4 to improve operational effectiveness and security. For example, right here is a diagram. Alice wants to send a message to Bob, okay? And they are going to use the BBA4 protocol. Alice choose first the random as the basis. That means he can send this or he can send this. He's going to be chosen by random. For example, on this example, he select the C basis, and the C basis is going to be transmitted to Bob. But Bob choose a random to detect if he's receiving the C basis and or the X basis. He have to detect it to perform the measurement. This is the new protocol called BBA4. That means everything is random from the beginning to the end. And the destination must assure how to read it and how to locate the message without any more information. Any question at this time? Is going too fast or too slow? It's fine for you? Okay. Okay, in summary, quantum communication and information network are promising areas in which secure data transmission and storage are implemented to the unique properties of quantum mechanics. However, such quantum systems face several challenges that impede their performance and practical deployment, including the noise, obviously, the decoherence that we mentioned at the beginning, right here at the top, and security vulnerability. Everything in quantum network must be 100% secure. How can we achieve that? With quantum key distribution. Right here is an example using Faraday. Okay, right here we have a Faraday that is going to transmit to station A, or is going to transmit to station B. Okay, and then we're going to learn how the station know what is transmitted to the other one, and all the information must be secure from the beginning. And this is the path, the step that is going to follow. A structured Faraday conduct QKD with ground station to establish independent secret key. That means the secret key of KA is for KA and KB, and the station bit doesn't know nothing about it, or vice versa. Yeah. They have to create a common key to be used as a pair of ground station. For example, station A and B, the Faraday will broadcast the bitwise parity for each individual key. The bitwise parity means that we are indicating if the numbers are even or are in pair. Okay, this is a way to. This is going to inform. Okay, I am transmitting in a pair to the other or a pair. Okay, now because the KA and KB right here, KA and KB are independent string, only known to each station. The problem is, hey, what we're going to do? They're going to receive the bitwise parity, but does not reveal any useful information anymore. That's all, only the bitwise parity. Then each station can obtain the other key for the station A, for example. To obtain the station B, it will determine the bitwise parity that he received of his own station using the broadcast KA inclusive OR and KA inclusive KB to obtain the KB. This is a methodology to obtain the other key that was never transmitted to them. Only was transmitted the bitwise parity. It's similar on station B. On station B, they don't know the KA, but they can obtain it with a similar method using all exclusive between KB and or parenthesis KA or exclusive from KB to obtain KA. This is to give you an idea of how the information, everything is on some kind of cryptography. Okay. Any question at this time? Okay, continue. Now, there is some kind of some also we can use hybrid networking. That means that we can use the old data transmission encryption that we are already using on internet, on the receiver and the on Alice and Bob. But we have a special channel also that is going to be optical. This is going to open our mind to use the both technologies as an hybrid technology. We are going to have researchers have demonstrated significant progress on experimental implementation by achieving secure key distribution over optical fibers and free space channels. And the other thing that they have is the quantum hardware advance. The quantum hardware advance, such as quantum memory, that the detector and single photon sources have been enabled developing more resilient with using the QKD system. Okay, that means everything is based on the QKD system, and this is this advance that they are at this time. They have some very well scalability and practicality are essential for deploying QKD in a large-scale communication network. This means that the researchers have implemented through security assessment to identify potential vulnerabilities and establish defense against attack. And finally, the other advance is the robust security framework and protocols. They have a bunch of protocols that have been developed for researchers on practical limitations such as side channels, intrusions, channel noise, and faulty detector. The objective is to detect any problem that we can have. That means, going back to the old one, they have to detect the external, the currents, and internal, the currents also. And for this, this example, this is the advances when using a hybrid network using the classical method, the classical channel, and the quantum channel. And they have obtained a very well result at this time. Okay, this is my reference. You want to study a little bit more about this process. Now, let's go to explain about quantum memory. Quantum memory are devices that can store the quantum state of a photon. That means they store the photon and they maintain that information onto the quantum carrier destination. To be more specific, we have a qubit right here. We're going to write on this memory. It's going to stay right here for a time that is going to describe by the user. Then it's going to be read for the destination. And this must be exactly the same as this one. Nothing can be altered. That means that we need to apply a lot of protocols to have coherent matter systems. That means that the information is stored inside the medium, cannot be lost due to the coherence. We need to be sure that this is going to maintain 100% confiability. And for this, we're going to show how the implementation is doing. Use a superconductor right here. And then in summary, the quantum error requires coherent matter system. They need to check for any variation from the beginning, what they are receiving, and they have to ensure that you're going to deliver exactly the same that we have it okay, after one time stored on the quantum memory. For these days, they are using a typical rare air ion dot crystals. This kind of crystal are very interesting matter because are used for quantum memories, owning their unique optical and spin coherence and properties at low temperatures. That means around 4 K. That is going to be on temperatures very cold. And they have to cool down the typical air ion array crystals. And they use a kind of cycle coolers that do not require any cooling liquids. Okay, this is very interesting. Usually, if we want to put something on the classical way, we use water or something like that. And right here, no, we don't use any liquid. They use a closed cycle cooler that can do that. This is the quantum memory. Okay, of course, this is very small. And this is a very important issue because the quantum memory provides a way to study how quantum effects works. That means that we are going to practice right there the entanglement, and this can be transferred between physical system or widely different nature. For example, between light and matter system, the different systems using the different matter. Okay, this was taken from this is my reference. To room. Okay, now as I mentioned at the beginning, I'm going to go back just to show you why I am following this. At the beginning, I said right here that we are going to explain the quantum internet as emerging technology. We already explained that. The quantum network problem that we have. And right here is what we are talking about, the quantum networking. This is the important request that you made to the Dr. Naran. Okay, let's go on, continue. Okay, this is a review, past review. Okay, this is quantum memory. And okay, one element, one device is the quantum memory. The other important is the quantum repeaters. And these quantum repeaters usually have the quantum memory integrated. And quantum repeaters are essential to extend the quantum communication capabilities by circumventing the constraint of quantum incoherence and particle loss in optical fibers. Okay. And you're going to make an example. I want to mention that the no-cloning theorems prevent direct quantum state amplification without annihilation. The quantum characteristic, even to signal amplifiers, can enhance signals for long-distance communication. That means that the signal sometimes is amplified, but we need to be sure that is a 100% copy of the original. These are the qubits, the information. And right here we have an array of well state analyzer to recheck that everything is going to be in place. And the one of this color is the successful EPR link attempt, and the one is on this color is the sacrifice for distillation. Okay, and these are the repeaters. Repeater station 1. That means I call it rare I minus 1, rare Ri, and rare I plus 1. Okay, in summary, an example, the linear network is shown with repeater station being equipped with a large number of optical active quantum memories or emitters all in one element. One example of linear network is shown with each repeater station being equipped with a large number of optical quantum memories or emitters. These memories emit photons, which are then sent to the station located at the midpoint of the link connection to the other two repeater stations. That means that we are sending to the station from this repeater to the one and from this to the other one. And everything must be assured that we are following the rules. At this midpoint, the station photon from two different repeaters are entanglement and measured together to effectively creating a pair links between the repeater, each repeater, denote Ri. Then they have multiple emitter memories located on both sides, and creating a spatial or spectrally multiplex parts. At the midpoint between any two repeaters, an array of Bell state analyzer, that means this one, what I already mentioned, exists to entangle photons coming from both sides. Only a fraction of the photon from either side survive the journey and reach the midpoint station right here. But anyway, we are going to ensure that the measure is going to be complete from the beginning to the end, and we are following the array of Bell state analyzer to complete the information. Okay, now I give you some idea of the quantum repeater with quantum memory. Right here is the linear method. We have the host, Alice. He wants to send a message to Bob, and he's going to use 1, 2, and 3 repeaters on linear way. That means this is the one that I explained right here. And the other one is the Bell statement measurement. When we have one memory module and another memory, the Bell state measurement is made. The primary function of the quantum repeater is to conduct entanglement swapping, to be sure that everything is entanglement. The basic is that one particle cannot exist without the other, and the behavior must be studied at the same time. And that means the distance is going to improve with the same quality. Now, to achieve this, multiple method for quantum repeater architectures. Multiple architectures have been proved. We have an example of only 2. Okay, yeah. And we have to be sure the quantum repeaters are essential for extending quantum communication capabilities by circumventing the constraint of quantum incoherence and particle loss in optical fibers. Okay, perfect, yeah. Now, the primary repeater protocols. The elementary repeater protocol, so it's a DLCC protocol, employ quantum memory at the intermediate nodes. For example, right here, right here, right here, to temporarily store the entangled qubits. Subsequently, the entanglement distribution range is successfully expanded by retrieving these qubits and entangling them with newly generated qubits. Now, one more is the protocol for entanglement swapping. The protocol for entanglement swapping, they are known also like long-distance entanglement. It's a key goal in the quantum communication to achieve the use of entanglement swapping operation. This operation integrates the entanglement swapping protocols, as I mentioned before, the BDCZ protocol, enable the formation of entanglement linkage between the multiple segments, thereby facilitating long-distance quantum communication. And then we also use the protocol dependent on purification. The protocol that enhances the fidelity of entangled state over extended distance, such as the quantum repeater with atomic assemblies, relies on purification. This protocol maintains high fidelity entanglement over multiple repeaters, not by periodically purifying linked state using local operation and classical communication, abbreviated like LOCC. That means local operation in classical communication is going to use periodically in its repeater. In summary, the challenge and future application of quantum repeater are the coherence and synchronization. We need to resolve this in 100% way. The coherence is the loss of quantum coherence or quantum due to the environment interaction. And we already mentioned that there is two kinds of the coherence. The coherence external and external. They are included right here. And the synchronization, the quantum repeater network to function correctly, quantum activities must be synchronized among remote nodes. All the information on this and this and this must be synchronized 100%. Okay, ready? Okay, in summary, on this slide, we are giving two examples of quantum repeater architecture. This is the linear, and this is the Bell state measurement. Okay, the one that is on the left side could be implemented on the one into the host and the repeater, between the repeater and the repeater 1 and 2, between repeater 2 and 3, and the repeater 3 and host. This is going to use the Bell state measurement. As is to assure the repeater are conducting the entanglement swapping. That means extend the distance on the entanglement, keeping 100% information secure and isolational. Any question? Okay. Well, now we're going to focus something different, the quantum entanglement sources. Quantum entanglement sources enable QES, enable technology that ensures secure communication, improving resistance to attack. And one especially is the quantum entanglement that generate entanglement photon pairs. To explain a little bit more this, it's going to be the entanglement is the foundation of the qubits. I explained at the beginning. For example, right here they have the qubits, and they have to be in the exact way from here to here. Right here we have a small polarization. Okay, this is bigger than this one. That means that we have a shift on the bottom sides. On the time being, all the information that we are reading is on the border, and sometimes for problems, the information is coming late or is coming early. We have to entanglement that can be realized for numerous physical properties. Yeah, and the key to realize quantum operation is maintaining coherence. The coherence of precision lies on the shell of the sphere. Right here, this is an old example of how they do it in the old times. They have the laser, they have mirror, this is the beam, another mirror, and we have the wave plate, and this is the crystal. This is the most important thing. The heart of the entanglement experiment is the crystal, because it's going to obtain two parts to be the entanglement, the one that is showing to the right and the showing to the left, and he's going to read all the information. Right now they are developing a very small nanostructures that is doing the same that we did on the old table. With all of this is integrated on this. This is right now, this is not available 100%. This is on the research and testing. What feature they have? They have on demand. They have high brightness with high degrees of entanglement. Okay, that means it's going to correct the polarization and going to correct time being. and the fidelity is greater than 0.97. It could not achieve the one this time. The line width is megahertz and gigahertz. The wavelength tunable is V-strain, and the per generation rate and G2O are the coupled to Poisson stats. That means that if we is injecting energy that is going polarized to in a vertical way, it's going to receive right here on the vertical waves and the vertical waves. If we're going to be horizontal, it's going to be the same right here and here. But what happened? I include the vertical and the horizontal to achieve the qubits. It's going to be right here, and using crystal, using rare air materials. This is an example of quantum entanglement source. Okay. As I mentioned before, at the beginning was a big implementation, and right now it's a very small, and is using superconductor also. Now, let's go to talk about the quantum entanglement generator. The quantum internet consists of quantum nodes and interconnect devices with various functionalities, including computation and sensing. It compromising between classic and quantum links. We connect the quantum node and form the critical network entities. The network entities that make up the quantum internet are physical network entities shown in the next figure. Right here, we have the entanglement generator. Sorry, okay, right here, and the generator include three different parts of the generator: the quantum node, featuring device, and quantum memory, the quantum link, and the classical link. And this is the beginning, and this is at the end. The quantum memory, this is what it's going to deliver using memory, measure the device, and quantum node. Now, okay, it's important to mention that the superconductive circuits are essential component for a disabled approach developing quantum processor. The quantum processor, I'm going to call it QPUs, the quantum processor, and they offer the necessary controllability and scalability for constructing large-scale quantum computer. Right now, they are building the entanglement generator using the element that I already explained. Now, the system relies on quantum characteristics of the superconducting qubits, including entanglement and coherence, to implement high fidelity on the all quantum processes in order to integrate superconductivity on the quantum processor into quantum network. It's imperative to establish effective quantum interfaces that can be transport quantum data between nodes while preserving coherence and fidelity. And again, they are repeating and making the focus that we need to preserve coherence and fidelity with all the elements that are used. Included, as I mentioned before, the superconducting qubit, entanglement, and coherence. Okay. Any question? On this slide, we are summarize what we explained on the other ones. For example, the classical link and the quantum link. For example, right here is implemented a kind of hybrid devices on quantum using the quantum link and the classical. As I mentioned on the last one, let me repeat it again, let me go back. Right here, the quantum channel and the classical channel. This is the one that we are showing right here. Okay, in this step. And we already mentioned the quantum memory, the measurement device, and the quantum node. The quantum node is including repeater right here. Yeah, we have time. Okay, then to finish, I want to make some examples. We are all the researchers are developing artificial intelligence, machine learning, and deep learning for advanced cryptography application. That means that they are focused on these 6 issues. Every quantum classic communication protocol bridges the gap between the classical and quantum communication system and allow the efficiency integration of quantum and classical information process technology. Because the technology is going too fast, sometimes we need to be sure that we have access to use the classical and the quantum communication system. Now, the machine learning as a part of the artificial intelligence models are trained on large amount of data from multiple sources. What does that mean? That means that we have to use a MPC. It is a subfield of cryptography. Beside that, we are going to use the homomorphic encryption and differential privacy to protect data privacy. However, these methods enhance security, performance, and accuracy. As we know, right now there is a kind of technology called generative models, like the one that we use every day in Windows is already integrated. And right here in generative models on quantum is going to generate quantum variation using autoencoders and quantum generative adversaries and network. I guess tomorrow you're going to have the artificial intelligence lectures. Maybe I can. You're not familiar this time. Tomorrow you have to connect what we saw today with what we just going to study on the next day. That means we have some different methods for use generative model. One is the variation of the encoder and quantum generative adversarial network. It's being developed to handle complex probability distribution. And another thing is the reinforcement learning algorithms. The reinforcement learning algorithms accelerate exploration of large state spaces and optimize policies and tasks like robotic control and game playing. And the quantum inspired deep learning architecture, like quantum neural network and convolutional network, are being proposed to tackle specific challenges in quantum information processing and simulation tasks. And the last mention I want to is the capability of quantum communication system have been improved by combination various artificial intelligence and machine learning and also deep learning. To make it clear, on this slide, we have a summary. Right here is the quantum blockchain. Okay, and we are using evaluating the classic models. We have decentralization, verification, and consents, chaining and entanglement, network quantum in the web. That means we are right here. We're using the internet, quantum internet, using the network, quantum blockchain future, data validity and data blocks, and cryptocurrencies mining. This is the technique that is already experimental to be released very soon. The quantum blockchain, and the other is the quantum machine learning. Okay, right here we have the data, and right here we're going to choose the topology, what kind of model of machine learning we're going to use. Then we have to use the quantum clustering and quantum deep learning, and process all the information on the quantum processors. And develop mathematical algorithms and superposition of states, and have the ability of search on all the information that we have available. This is in the process of being developed. And is for what? We want to achieve advanced cryptography application. Okay, now we need to develop strategies for improving security, reliability, and performance using the quantum neural network and quantum autoencoders. This is from the side of artificial intelligence. The QNN, that means the quantum neural network, the performance relies on the principle of quantum computing, superposition, and entanglement. This means from the classical quantum mechanics, it's on the quantum computing, and this includes everything, superposition and entanglement. And we are using quantum autoencoder that can learn to detect a correct spatially correlated computational error. This is an example using random forest and the one class SVM. We have the network traffic. Okay, we're talking about the cryptography application. We have the network traffic flow information on the entry, and we're going to dimensionality is to height. We're going to reduce it using a number of qubits available. Okay, that means that we're going to keep all the information, encode input to the quantum state. Then we're going to encode and then apply the algorithm that we use on artificial intelligence or machine learning. Now, this is a very important table right here. The comparison between quantum cryptography approaches using with or without machine learning and deep learning. The QKD protocol selection has been approached with machine learning and deep learning using a tree CNN model. And if we do want to use the machine learning and deep learning, this convolution network, and this is using traditional method, but using machine learning, we have higher accuracy, and the time is reduced, and that means that security is enhanced. If we use the traditional method, okay, it's going to be, the precision is going to be less, and we're going to use more time, and the security is not excellent. That means that using the QK protocol selection, using the tree convolution network, we have achieved some very great results. For quantum error correction, we are using quantum autoencoders, but if you want to compare with the classic method, we improve a lot the accuracy, we improve the speed and the security. Another is the cryptographic key generation. For that, they are developing a machine learning enhanced algorithm. You don't want to use this. You are going to use the standard algorithm, but you are going to lose efficiency. You're going to be more time and less secure. And with machine learning, it's going to be more efficient, quicker, and more secure. Of course, that the speed is an issue on quantum network. And right here we have the post-quantum cryptography using our artificial intelligence enhanced algorithm, which they have improved over the classical algorithm, higher accuracy, the computation time is reduced again, and the security strain is enhanced. And the quantum key distribution that what we explained right here using machine learning models, the enhanced QKD, usually the standard, we have a very higher accuracy, a very reduced time, and very enhanced. Okay, this is the direction that they are following on the quantum using artificial intelligence, machine learning, and deep learning for cryptography application, and the results seems to be excellent. Okay, yeah. So in summary, what we studied today was the quantum key distribution. That means the elements of the quantum network requirements. Every quantum network requirement needs a quantum key distribution. That means that all the protocols to maintain information from the original to the end is going to be always checked and maintained. The query repeaters, as we show on the diagram. Okay, I have 2 minutes. Okay. And the quantum entanglement sources that we already explained using the quantum entanglement generators. And I made some example of artificial intelligence and machine learning for improving efficacy and security of quantum communication. Okay, and we explain on this lecture the quantum repeater architecture. I showed only one of them, the linear, with the Bell verification, the quantum internet protocols, and the quantum key distribution. They focus a lot on quantum key distribution. We highlight the importance of quantum computers using artificial intelligence and machine learning methods and blockchain technologies in quantum network, and discuss the potential application in conflict zone and real-world application. That means this is growing. This is an area that is growing exponential. Okay, with this I'm going to finish my presentation. I don't know if you have any question. I really appreciate your invitation, and I hope that it's going to be clear to maintain the focus on what we need to learn, what we need to focus our research to develop the quantum network requirements at this time. Thank you.
Thank you, sir. Before we conclude, dear participants, do you have any doubts or queries about today's session?
I know that it's a lot of information, but you already record the lecture, and if you request me, I can send you the slides, and you can read it slowly.
Yes, sir. So, assuming no one has any doubts, and as we conclude another insightful session of the 5-day International FTP on Future Generation Networking, it is my privilege to extend a warm and heartfelt vote of thanks. First and foremost, I would like to express our profound gratitude to our distinguished speaker, Dr. Jorge Garza-Ulloa, for his exceptional session today. His deep expertise in quantum networking has provided us with valuable insights and open our minds to new possibilities. Your discussion on quantum networking as a new frontier in communication, the quantum internet, quantum communication, quantum network problems, memory, quantum repeaters, and quantum entanglement sources has been truly enlightening. The knowledge you imparted today has broadened our perspective on the future of networking and its immense potential. Dr. Garza, we sincerely appreciate you taking the time to share your knowledge and experience with us. Thank you, sir.
Thank you very much to all attendants, and my heart is with you, and we hope to work together and maybe in the future, and develop something useful that everybody needs at this time. Thank you, David, and hugs to everybody, and I hope I open your direction on the research, and thank you very much, and hugs to everybody.
Thank you, sir. I would also like to extend my appreciation to the organizing team for their relentless efforts in making this FTP success. Finally, I would like to thank all our participants for your enthusiastic involvement.